Hello and welcome. In this video, we're going to focus on how to graph an exponential function, how to identify and use transformations of exponential functions, which is going to tie back to transformations of really any function that we've been discussing throughout the entire course, and how to write a transformed exponential function. And then we're going to wrap up by talking about what the graph of the inverse of an exponential function looks like and what the name of that type of graph is and how to use that to graph. So let's go ahead and jump right in. So in previous lessons, we've talked about determining if an exponential function is growth or decay, and we talked about if it's of the form ab to the power of x, we can look at b being greater than 1 as growth and b being less than 1 as decay. We also talked about how the graph of growth and decay kind of looks like a skateboarding ramp, where you can see that you're going uphill for growth or downhill for decay. So knowing these pieces of information will help us get an idea of what our graphs should look like. Then, just like with any other function, we can start by making a table, plugging in values, and sketching that graph. So 2 in this case is our b value on number 1, which is greater than 1. So we know that since b is 2, which is greater than 1, we're going to be graphing exponential growth. And then I'm going to go ahead and I'm going to make a table. And I'm going to just plug in some easy numbers to plug in: -3, -2, -1, 0, 1, 2, 3. And I'm going to plug those in. 2 to the power of -3 is 1 over 2 to the third, which is 1/8. 2 to the power of -2 is 1 over 2 squared, which is 1/4. 2 to the negative first is 1/2. Anything to the power of 0 is 1. 2 to the first power is 2. 2 squared is 4. 2 to the third is 8. And now I can go ahead and plot those points. And I probably don't need to plot every single one of these fractions. The goal is that I'm getting the shape as best as possible. So let's see what we can fit on this graph. It looks like we are going to be able to fit 3, 8. And I'm going to go ahead and graph those other integer points: 2, 4, 1, 2, 0, 1. Now for these fractional points, I just want to remember how the graph of exponential growth behaves. So it's going to be getting closer and closer to this x-axis, where we're going to have a horizontal asymptote. So I'm going to make a note that there is an asymptote at y equals 0, which means when I plot these remaining points, I'm going to get closer and closer to the y-axis, to the x-axis, but I'm never going to cross it. So let's go ahead and connect those dots. And there we have it. So make sure you have arrows on both ends, because we're allowed to plug in any number. Make sure that your graph is not crossing the line y equals 0 or the x-axis, because it's approaching it, but it never gets there. All right, I'm going to encourage you to pause the video and go ahead and make a table for number 2 on your own, and then unpause the video and see how you did. All right, so in this case on number 2, b is 1/2, which is less than 1, so we're looking at exponential decay. Our table is almost going to be like the reverse of the table that we just had. 1/2 to the power of -3 is 8, because you take the reciprocal and apply the exponent. I'm going to add my horizontal asymptote at y equals 0. And then I'm going to go ahead and plot those points. And now I should be looking at a downhill slope getting closer and closer to the line y equals 0. And there I have my graph. Not crossing the horizontal asymptote, approaching infinity up on the left, because it's getting bigger and bigger as we go to the left. Okay, now just as we learned in previous chapters, we can always use the parent functions to graph. With exponential functions, the parent functions are different based on the different base values. These are both parent functions on examples 1 and 2. Example 1 is the parent function y equals 2 to the power of x. Another version of that function could be y equals 2 to the power of x plus 1, and this would be a translation up 1. Or if we wanted something happening in the exponent, this would be a horizontal translation to the right one. So transformations are going to work the same way as they have in previous units, but the parent function, there are an infinite number of parent functions, because we could be looking at different base values. So let's just refresh our memories on what transformations look like and see some examples with exponential functions specifically. All right, so just as I mentioned, And I think for all of these, we chose to use the base 4 just so it's easier to see. Translations left or right are going to be up in the exponent. So -3 would be 3 to the right, +2 would be 2 to the left. Vertical translations are going to be down outside, just as always. Up means plus, minus means down. Reflection over the x-axis is going to be in front of the 4, just like always. Over the y-axis is going to be in that exponent with x. So just notice that difference. Stretches and shrinks horizontally, they're going to be up in the exponent. Vertically, they're going to be in front. And make sure you don't actually multiply this. This 3 and this 4 can't multiply to be 12. That violates the order of operation. So you're going to see a number in front and then parentheses either around that number in front or around the exponent portion of your function. So if we know the parent functions, we can use that to help us graph. So we actually just graphed this, f of x equals 1/2 to the power of x. Now we're going to move all of those points down 4. So let me just put that table back up for y equals 1/2 of x, and then we can use that to graph our function g. All right, so here's the parent function that we already graphed on number 2, f of x equals 1/2 to the power of x. We still have our horizontal asymptote at y equals 0 for that function. So now we're going to look at g. Transformation-wise, the only thing that's different from f to g is this -4, which we know means that we are translating down 4, which means what we can really do is just take each of the points that we just graphed and move them down 4. So this point here is going to go down 1, 2, 3, 4 to here. This next point that was right next to that is going to go down 4 to here. So we can move each point down 4. Another way that you can think about that is you can actually use the exact same table, -3, -2, -1, 0, 1, 2, and you can actually subtract 4 from each of these y values to get your new y value. So that would be 4, 0, -2, -3. Some fractions, but not that big of a deal, -3.5, -3.75. So that's going to give you an idea of all of the points from your graph. This also means that our asymptote is going to move down 4. So originally we had an asymptote in our parent function at y equals 0. Now we're going to have one at y equals -4 because that is how our graph has translated vertically. So that's going to be our asymptote for our function g. So go ahead and graph a couple more points so you get an idea of the shape and then connect. And there we go. So we have the same basic shape, and mine is not connected perfectly, but same basic shape except it's shifted down. Every single point is shifted down. Now for number 4, I'm going to have you go ahead and graph your calculator so that you can evaluate E or approximate it enough to graph it. So E is not something we're typically going to graph without a calculator or with that. We're going to be approximating nearly everything. But I'm going to go ahead and put a base table down for you, and I'm going to have you pause the video and practice using your calculator to evaluate E at each of these values, and then unpause the video and see how you did. All right, so hopefully you had time to practice using your calculator to evaluate E at these different values, and you came up with approximately what I have in the table here. And we're just going to graph those points to the best of our ability, knowing that they're not integers, so our graph isn't going to be perfect, but we are going to include that horizontal asymptote at y equals 0. So there is my sketch of this graph here. Now, let's identify from the equation what our transformations are. So there's two things happening. This +3 means that we are translating 3 to the left, and the +2 means that we are translating up 2. So again, you can take each of those points and move them 3 left and up 2, whether you do that with your table or you simply just do it on your graph. This time, I'm just going to do it on my graph. So go ahead and pause the video. Make sure when you do that new graph that you also translate your horizontal asymptote up 2. And there we have our graph. Now, we're probably not going to spend a lot of time graphing E by hand because, again, it's an approximation, but being able to identify those transformations and knowing what the shape of the graph of E to the power of x looks like is important. So now that we've talked about graphing and identifying those transformations, let's practice transforming functions. Now remember, the most important thing about writing a transformed function is checking that the order is correct, and if it's not, dealing with that appropriately. So we're going to practice writing it in function notation and then also writing it in applied to the function f of x. So let the graph of f be a translation or be a reflection in the x-axis. What does that mean? It means we're going to take the opposite of our function, a reflection in the x-axis, followed by a translation for right. Well, the reflection in the x-axis doesn't affect the for right, so I can just put x minus 4 inside of the graph f of x equals 2 to the power of x. So our transformations were out of order, but it didn't matter because one of them was a vertical, affects the vertical components, and one of them affects the horizontal components. So let's apply this to our function f. F is the function 2 to the power of x, except now we're going to put a negative in front, and in the exponent, we're going to substitute in x minus 4. So here is our transformed function. I'm going to encourage you to pause the video and work through number 6 on your own, and then unpause the video and see how you did. All right, let the graph of g be a horizontal stretch of 3. So what does that mean? That means inside we're going to plug in 1/3 of x, followed by a translation 2 units up. So again, we have things out of order, but it doesn't matter that they're out of order because only one thing was horizontal and only one thing was vertical. So what does this look like in our function? Well, f was e to the negative x, so I'm going to just rewrite e to the negative. What are we substituting in for x? We're substituting in 1/3 of x, and then we're going up 2, so out here we're going to have a plus 2. So here is our transformed function. All right. Now that we've talked a little bit about how exponential functions look on a graph, how to identify their transformations, let's see how that looks if we tie it back to the idea of an inverse. All right, let's see how you're doing with graphing exponential functions. Go ahead and graph the function f of x equals 3 to the power of x. Make a table. This is a parent function, so you can't use transformations to graph it, but just plug in some values and see how your graph looks. Then unpause the video and see how you did. So here we have the graph of y equals, or f of x equals 3 to the power of x. So I'm going to come up here, since I'm going to graph more than one thing on this axis, I'm going to label this. Now, as a reminder, the next thing we're going to be asked to do is to graph the inverse on the same graph. Well, what do we know about the inverse? The inverse switches our x and our y. So if we're graphing f inverse of x, I'm going to have 1/9 negative 2, 1/3 negative 1, 1, 0, 9, 2, 27, 3. That point's not going to fit on there. But go ahead and pause the video and graph those points. Now, before you connect, remember that these two graphs should be symmetric about the line y equals x. So if I just sketch this going there, it's like I should be able to fold that graph. What that means is I'm going to have an asymptote for this graph as well, except instead of being at y equals 0, it's going to be at x equals 0. Because the domain and the range are switching. And when I connect, I'm going to make sure that my graph is getting really, really close to this x equals 0, but it's not crossing over it. So there we have our sketch. Now this function, the inverse of an exponential function, it actually has a special name, and that is a logarithmic function. And what we're going to do in much of the rest of this unit is explore how logarithmic functions work and how we use them. So a logarithmic function, let's just get some basic information about it here. A logarithmic function is the inverse of an exponential function. Special name, logarithmic. We refer to them as logs for short. Now, we will talk about how these two functions relate together and their specific properties of logs that relate to properties of exponents. We will focus on that in a future section. Today, we really just want to focus on using the exponential function to graph the logarithmic function. So we're going to hit on a couple of key things, and then we're just going to wrap up by doing a few more practices of graphing the inverse simply by starting with graphing the exponential function. So if This is a really important property, and it's going to come into play a lot in future sections, but for us, it's just important to be able to translate between these two forms. So if we had something, actually, let's use the one we were just looking at. If we had something like y equals 3 to the power of x, if we wanted to translate that into logarithmic notation, that would look like log base 3 of y is equal to x. So the base of our exponent becomes the base of our log. So we say log base this of whatever is on the other side is equal to the exponent. A log is an exponent. So your equal to is going to always on the right-hand side, or this is always going to be equal to the exponent. These are exactly the same thing. They're just written in two different forms. And we're going to use the translation between these two forms to help us out when we're graphing in this section. So because logs and exponentials are inverses of each other, we can use that symmetry that we know exists over the line y equals x to help us get that shape. We can still see growth versus decay, thinking about if we're going uphill or downhill based on the graph. And we can still observe that we're going to have now for our logarithmic graphs, we're going to have vertical asymptotes at y equals 0, and that's going to change our domain and our range as well. So let's actually jump into looking at an example together, sort of similar to what we just did on number 7, where we are going to graph a logarithmic function by first finding or evaluating values in the original function, the exponential version. All right, we are going to learn other ways to graph logarithmic functions later, but for right now, what we're going to do is we're going to rewrite the log statement as an exponential statement. We're going to find the inverse. So switch our x and y and find the inverse. Then we're going to flip our table for the inverse for our exponential functions to make the table for our original function. And then we're going to graph and make sure we're not forgetting our asymptotes. So what in the world do I mean by this? The first thing we're going to do is say let y equal f of x. And we're going to so that's going to be log base 2 of x. And then we're going to be looking at the inverse because we know how to graph an exponential. So we're going to say x equals log base 2 of y. Then we're going to translate this into exponential form. So log base 2 means 2 to the what? 2 to the exponent, x, because a log is an exponent, is equal to y. So we're going to make a table with 2 to the x equals y. And we've already done this in this video, so I'm going to just plop it in here, actually. There we go. And then more importantly, now that we have a table for our function, or for the inverse, for the exponential, we can flip our x and y coordinates to have a table for the log. So instead of negative 2 1/4, we have 1/4 negative 2. 1/2 negative 1, 1 0 2 1 3 2 and 8 3. So I'm going to go ahead and fill in the rest of those points. There we go. Now I know with a logarithmic function I'm going to have a vertical asymptote when x is equal to 0, and now I can just plot these points. And once I've plotted them, I can connect and make sure my graph is getting closer and closer to the x-axis without crossing it. So this is our function. Now again, we're going to talk about strategies for graphing this differently in future sections, but for right now, our goal is just to say, what does this look like as an exponential function? We're still getting comfortable graphing those, and then flip our x and y so that we can graph them again. So looking at number 9, let's talk about the inverse, the exponential first. So I'm going to say let y equal g of x, which is log base 2 of x plus 1. To find the inverse, we're going to switch our x's and our y's. So x is equal to log base 2 of y plus 1. And now we're going to solve for y. So we're going to subtract 1 on both sides. Now, over here on the right, I just have this log. So now I can translate a log is an exponent. So I can rewrite this in exponential form. 2 to the power of x minus 1 is going to equal y. Now to make this table, we can use the table we just did. We're just going to decrease all of our x values, or we're going to increase all of our x values by 1. Or you can simply just plug in the same values that you did before. You could plug in -2, -1, 0, 1, 2, 3. I'm going to start at -1. I'm going to plug in 0, 1, 2, 3. I think that's going to give us enough. And again, you can use the table that you made on number 8 since this is based off of the same parent function. You could also use the table that we made in number 8 for our log function and simply move all of those points up 1 to get our new points, because how is this different than this function? It's translated up 1. But we're going to focus on transformations of logs in a different video. So if you're not ready for that yet, that's okay. Go ahead and fill in this table for g and then rewrite your table. And actually, this should say g inverse. And then you can go ahead and rewrite table using what we're actually looking for, which is g of x. I'm going to go ahead and add my asymptote here. So go ahead and fill in those two tables and graph those points. And there we have that graph. If you're feeling confident, go ahead and do number 10 on your own. If you're struggling to set up the inverse, then follow along with me. So we're going to say let y equal f of x, which is -3 natural log of 1/2 of x. So to find the inverse, we're going to switch x and y. So x equals -3 log base 1/2 of x. To isolate the log, we're going to divide both sides by -3. And now since a log is an exponent, we can switch forms. 1/2 to the power of -x over 3 is going to equal y. Now, when you're picking values to make your table, you may want to pick multiples of 3 so that they divide evenly. So I would recommend -9, -3, 0, 3, 9. But now that I helped you out with that part, see if you can make a table and then flip that table for your inverse and go ahead and graph it, including your asymptote. Then unpause the video and see how you did. And there we have our graph. So we will do much more practice with those, and we'll talk about in future videos different ways to graph logarithms, but I think that was a good introduction to the idea of a log being the inverse of an exponential function. So what do we do in this video? We talked about how to graph an exponential function using a table, plugging in logical values. We tied that back to the idea of transformations. How can you use the transformations and what do they look like with exponential functions? And how do we apply or write a transformation of a function? And then we wrapped up by tying that to the idea of the inverse of an exponential function, which is a logarithm, which we're going to dig into more in the next video. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.